All right. So, here we go. So today we're going to talk about Ekman convergences in the Gyres pressure, which is related to what we talked about last time with the Ekman transport in particular. And so the Ekman transport is interesting in and of itself. Like it carries stuff around, typically to the right of the wind in the northern hemisphere, to the left of the wind in the southern hemisphere. But it's even more interesting when it kind of converges or diverges into a region or out of a region. So we're going to start thinking about what that means in terms of the sea level, in terms of the pressure surfaces, and also in terms of just the transport of stuff around, which maybe will stimulate some ideas for your paper too. Um, and so the next thing to be worrying about is the response, which is due tomorrow. Um, so I hope everybody has found their peer reviews, seen them, looked at them. Have there been any problems with that? Okay, cool. And like I said last time, the calling book, chapter 3, is actually really helpful for this because it has lots of good graphics, some of which are in the slides, but some of which are not. So that's a good place to go and think about these kind of balances. That will continue to be a good reference even as we go into geostrophy on Thursday. Okay, so we're reviewing our balances again. The hydrostatic balance is a vertical pressure gradient versus gravity. Um, the Taylor-Proudman theory involves three different terms, but it stiffens the flow when friction and density variations are not present. And it means that things don't shear in the direction of the rotation axis. Inertial oscillations are balanced between just the Coriolis and the time derivative. All the other terms are taken to be small to get pure inertial oscillations. And so you can think of this in terms of the Ekman number and Rossby numbers, which I'll come back to in a second. And then there's the Ekman layer balance, which is the one that we started to talk about last time. It's between the Coriolis term and the friction term. And it turns out that the important part of the friction term for the Coriolis will be the vertical derivatives inside of the Laplacian. And that's the one that we saw that Ekman actually did a analytic solution with a constant viscosity, but the vertical integral of that is actually more useful for what we're going to continue to talk about, which is this Ekman transport. Okay, so let's pause for a second. Are there any questions about how to do the response to your reviews, or does anybody have any other issues or things they wanted to raise about that? Have people been spending a lot of time on the response or fairly quick on the response?
An interesting amount of time.
Yeah. So the response is only worth 3 points, whereas the first submission was worth 10 points. So you should be careful not to use a huge amount of time on the response just to kind of keep yourself sane and prioritize things. Um, it's always a good opportunity to look for a finesse. Like if a reviewer says, can you prove to me that such and such? One one response is to say, assuming such and such in the paper rather than proving it, which is sort of it's something you might not really choose to do, but in order to keep the time limited, that is an available opportunity to you. So that's something you can do. And then, like I said, there should be 3 documents that you should upload. There should be a response to each of the reviewer comments, or at least the major comments. It's okay to say you just corrected all the typos that were pointed out. You don't have to do those point by point. Then a version of the paper showing tracked changes from the version that you submitted last time. And then just a clean version that's like ready to be uploaded into the proceedings that doesn't have track changes. So that's what you upload 3 different PDFs to the into the response on Canvas. All right, cool. So the first thing I wanted to talk about today is a little bit more about non-dimensionalization and like the procedure for non-dimensionalization. we've been talking about the Rossby number and the Ekman number kind of hand wavy. I wanted to show you a little bit more precisely how you can get those out of like the momentum equation. Um, and then from there, we'll keep doing that and we'll start to think of like rapid rotation or strong friction in terms of non-dimensional parameters as we go on. We'll start to have an equivalency built up in our heads between those pieces as we go. Um, then we're going to go back and review the Ekman theory a little bit. We're going to review the hydrostatic pressure theory, and then we're going to put those together into an Ekman plus hydrostatic pressure to get an anticipate the patterns of pressure that are going to be in the gyres. And we'll see that it's actually pretty similar to what the patterns of pressure are in numerical models. Okay, so non-dimensionalization. So we've done this a couple times. I wanted to do it a little bit more slowly because we have a little bit of time, extra time today to cover it. So the procedure here is first you estimate the size of each of the terms in terms of like the fundamental dimensions, like the time scale, the length scale, the velocity scale, and the vertical length scale, and so on. Most of the time, you're going to be able to do it with just those, plus maybe some parameters like the Coriolis parameter, the magnitude of it, the magnitude of acceleration of gravity, the background density, and the viscosity. Those kind of extra parameters will come outside, plus these kind of time scales and length scales. So then step two is that you scale all the terms in the equation by these set of parameters. So for example, the first one goes like a velocity over a time scale, because that's the change in velocity over the change in time. So you could say, well, if I say that the velocity scale I'm thinking about is about the size of the change in the velocity, and the length scale I'm thinking about is the amount of time that it takes to make that change, then this term would scale like a change in velocity over a change in time, or just velocity over time. Similarly for all the rest of the terms. And then this is the part that we have been doing not so formally, is collect them all together and put them into non-dimensional pieces. So if I take that first step and pull out a velocity scale and a time scale out of that first term, this little asterisk means I've just divided the real velocity by that velocity scale and left a dimensionless velocity. And this is the same for the time. Like I've rescaled time in units of whatever the time scale big T is. So I can do that for the first term, and I get this little thing, which is just these parameters on top of each other. This still has dimensions of acceleration. It's not a dimensionless quantity yet. Similarly, I do that for this term. I pull out a velocity squared and a length scale. For this term, I have the Coriolis parameter times the velocity scale. For this term, I have a pressure scale, which I'll talk about a little bit more in a second, but the pressure scale, that's a pressure scale which already includes the density part. So pressure scale and then a dimensionless pressure over here. And then the derivative has a 1 over length scale in it. And then the last term, you have the viscosity coming out of velocity over a vertical derivative, which we said was the more important one. You could actually add onto this of viscosity times the velocity over a horizontal length scale squared. But that term would be a small correction to this one. Why is that? How big is vertical scale versus horizontal scale in the oceans?
Very small.
Very small. There we go. Right. Because the oceans are only like 4 kilometers deep, but they're like 10,000 kilometers wide. And it's even more of a shifted aspect ratio, a small aspect ratio when you're thinking about just the Ekman layer, which is maybe 100 meters or 10 meters deep and 10,000 kilometers wide. So if I'm dividing by a big number, I get a smaller number. If I'm dividing by a smaller number, I get a bigger number. So this is the dominant term out of this derivative, which has both horizontal and vertical derivatives in it. Okay, so now we're expecting the Coriolis term to be important always, and because we're in rapidly rotating fluids, because that's what we decided to do. So I'm going to take this factor of F times V, which has the units of acceleration, and divide every term by that factor. And so then I just get Z hat cross the dimensionless velocity is my Coriolis term. I get 1 over F times time in here because the V cancels with this V and the F stays there. This one I get V over FL, which is one of the V's here cancels out, and then the F goes in the downstairs. I get the power, I get the pressure scale over V times F times L, and then I get the viscosity over F times H squared for this one. So maybe these look familiar, this one and this one in particular, we've been talking about since the beginning of class. Those are just the Rossby number, temporal Rossby number, the Rossby number, something funny called the Euler number times the Rossby number here, and then the Ekman number. So by just collecting those dimensional terms out front, we see that these dimensionless ratios we've been talking about actually appear as the coefficients of the terms in the equation. So how big is this term versus this term? Well, it's obviously this one is Rossby smaller than that one, assuming that we did a good job of estimating the velocity and length scales. How big is this term versus that one? Well, it's temporal Rossby versus that one. How big is this one versus that one? Well, it's Euler number times Rossby number, and this is Ekman number times Rossby number. So when we think about our dominant balances, it's pretty easy now to read off that so the Ekman layer, which is a balance between the Coriolis one and the friction one, is when the Ekman number is order 1 and all these other coefficients are small, and so on. So if we go back, so if these are just the ratios we've been talking about, and here's the new one, the Euler number, the pressure change over the momentum advection. But we've been talking about these kind of how to interpret them, like it's the momentum versus the viscosity, or the momentum versus the Coriolis, or the momentum versus the Coriolis, so on. Here's just the ratios of what those terms are in terms of velocity scale, length scale, viscosity, and so on. And so those are the things that we're giving names, and it's because they appear as the coefficients in the equations after you non-dimensionalize the equation. So when we go back to our balances, now we can say Taylor-Proudman exists when the advective Rossby number is small, the temporal Rossby number is small, the non-conservative and non-barotropic densities are neglected. So you could say the Euler number is small and the Ekman number is small. That's what this balance, when that balance is the dominant one that's left over. Similarly, the inertial oscillations are within an advective Rossby number that's small, an Ekman number that's small, and a temporal Rossby number that's order 1. The Ekman layer, advective Rossby number small, temporal Rossby number small, Ekman number order 1, and so on. Hydrostatic balance turns out to be just about the aspect ratio of whether the horizontal versus vertical, which one is giving you more of the pressure. The pressure is coming mostly from the gravity term, and so that one comes really just from the assumption of a small aspect ratio. Okay, so are there any questions on that non-dimensionalization before we move on to the next, back to review Ekman? Okay, doesn't sound like it. So remember, Ekman is a balance of our rotating momentum equation. So this one doesn't have the rotation in it. But we're going to need the Coriolis term to balance something on this side, maybe the pressure gradient, maybe the whatever. That's what we are going to think about as our Coriolis balances, our rotating balances. And so the focus here is really on what happens when the wind blows on the surface of the ocean. There's a small layer, and we know that the small layer isn't full depth of the ocean because we cranked through and estimated an Ekman number. The Ekman number is really only 1 within a few tens of meters of the surface. And that small layer sits on something below, which might be a Taylor-Proudman interior. Taylor-Proudman interior doesn't have any vertical shear because that's it stiffens the fluid. The rotation stiffens the fluid. But when we bring the friction in, which happens in the Ekman layer, where the Ekman number is order 1, then the friction does play a role. And so we can have some vertical shear, some shear in the rotation axis direction. And so we're really focused on the difference, this little extra velocity we get in within the Ekman layer, and we're calling that the Ekman velocity, this extra excess of sheared velocity that goes up just in the Ekman layer at the surface. If we integrate over this, we know that there should be, at the bottom, the effects of turbulence and friction are negligible. At the top, the wind is an input. And so the only other force we have that could really balance the wind stress, if there's, is the Coriolis force. So if we hypothesize a balance between the Coriolis force acting over this whole layer, all these sheared velocities, but integrated in the vertical, and the wind, however much energy, how much force the wind is exerting at the surface, then we find that we need the depth integrated velocity here to be going perpendicular to the Coriolis force in order to give us a Coriolis force going in that direction, which means it's also perpendicular to the wind. So that's the Ekman transport. Perpendicular to the wind direction, perpendicular to the Coriolis direction, so that the wind and Coriolis are opposing one another. And the wind in at least the northern hemisphere, the Ekman transport in the northern hemisphere is 90 degrees to the right of the wind direction. We said, well, what is this little viscosity? Well, the viscosity is really, it's kind of the idea that eddies, turbulent mixing, and within the mix layer might behave just kind of like molecules. And if the molecules are moving from a fast moving part of the flow into a slow moving part of the flow, or from a slow moving part of the flow into a fast moving part of the flow, they would tend to blur out the velocity differences. The fast moving ones would speed up the slow part, and the slow part moving ones would slow down the fast moving one. And so this operator, this Laplacian operator, in fact, really does that. So when we see the form of the friction that looks like this, or the eddy viscosity that looks like this, you can think about this friction being not only a viscosity times a Laplacian, but it looks something like this. It's proportional, aside from the viscosity part, to the differences in the velocity, the velocity to the right in x minus the velocity to the left in x minus 2 times the velocity at the center. It's like we're kind of thinking of this as a grid, plus the same thing in y. This is just a discrete form of the second derivative in x, this one, and this is a discrete form of the second derivative in y. And so look at that for a second. That says, take the velocity at the center of the cell. There are actually 4 of them, but there's a 2 downstairs, so it cancels out. So there is the velocity at the center at location x and y. It's the deviation of that from all of its neighbors, the average of the neighbor to the right, the neighbor to the left, the neighbor to the north, the neighbor to the south. So you're asking, how different is the velocity in the middle from all of its neighbors? If the velocity in the middle is bigger than its neighbors, then this viscous term will tend to decrease the velocity in the middle. If the velocity in the middle is smaller than its neighbors, so this is a positive term, then it will tend to increase the velocity and make it closer to its neighbors. So what this Laplacian operator is doing is it's doing this smoothing out of the anomalies in velocity, but it's doing it in all directions at once. It's doing it in the x direction, the y direction, then this sort of horizontal expression, but it's also doing it in the z direction. So wherever there is a shear in the flow, this friction term is trying to reduce the shear. It's by slowing down the fast anomalies and speeding up the slow anomalies. So I hope that makes sense. That's like the process. This is the calculus form, and this is the kind of the discrete or sort of like deviation from your neighbor's form. They're all kind of telling the same story. Sometimes it's nice to think of this not like this as a Laplacian, but as the divergence of a gradient. And so the viscosity normally goes inside. So this viscosity times the gradient of the velocity, this is called the viscous flux. So this is a flux divergence, the same way that we had a flux divergence of salinity fluxes and a flux divergence of heat fluxes. This is a flux divergence of momentum. Um, and it's a flux divergence of viscous momentum. So the viscous stresses are a transport of momentum from place to place. And when they diverge, you can either accelerate or decelerate the fluid at that location by the divergence of the viscous stresses. Okay. So it's a divergence of a viscous flux is the Reynolds stress, or it is the eddy viscosity. If we want to step back, we said that the eddy viscosity might be a poorer approximation. You could do this instead in terms of the Reynolds fluxes. And this is only for the folks who've done some turbulence averaging kind of conversations before in other classes, other fluids classes. You can express this same eddy flux as a divergence of a Reynolds stress like this. So the divergence of an eddy flux, divergence of a Reynolds stress. And so this eddy viscosity parameterization is really saying that the Reynolds stress is approximately a viscous stress. And so for some of you, that might make sense who had fluids before. This is sort of an extra detail. But what I mean here by the prime is like small scale turbulence is represented by the primes. And then I'm averaging over the collective effect of those primes with the overbar. That's the same in this equation, this equation, this equation. So the Reynolds stress is the averaged effect of all the small scale perturbations. So not only is the viscous reducing anomalies, but it kind of mimics the co-varying effects of anomalies within the fluid that have to do with those eddies. That's what we're trying to do with this eddy viscosity effect. Okay, so this is from last time. We said, okay, we can balance the Coriolis term for that velocity anomaly, that V extra, the V Ekman that's in the Ekman layer. And the only term that's really there to balance that extra that's new that causes that shear is the viscosity, the eddy viscosity on the V extra. The only term that's sheared in the vertical is the V extra. So you could say that's the total V, but it's really the V extra here. So, and the V extra is the total velocity minus the vertically averaged velocity like this. And so that here's the scaling from that Reynolds stress that I just showed you a second ago. And here is the Ekman number, which we're saying is equal to 1 in order to have this balance work. So the Ekman transport is the most robust part of this, which is really the vertical integral of that V extra, which if you work out how it depends. So the surface condition here gives us the surface boundary condition on the viscous stress, which is equal to the wind stress. And then these factors down here is just the F that's coming from the fact that this is a Coriolis term, and the rho is just what you needed to be there to cancel out with the units of the stress at the surface. So tau over rho is the boundary condition on the kinematic viscosity times dV extra dz. So this is the Ekman transport written out as an equation rather than as a force balance. And there's a northern hemisphere version, which is this one, which is when F is a positive number. And there's a southern hemisphere version, which is when F is a negative number. And so the negative number just flips the relationship between the wind stress and the vertical direction, which means that instead of 90 degrees to the right of the wind, you're going 90 degrees to the left of the wind in the southern hemisphere. Okay, and so if this is all we need, maybe we don't even need the spiral. All those details within the Ekman layer are probably not that important for large-scale oceanography. And this would work just as well if I use the Reynolds stress formulation. I could write that whole thing before and not even make a viscosity approximation and still get this answer. So this works even for very complex turbulence. This relationship is true regardless of the eddy parameterization or something like that, the eddy viscosity assumption that we had before. So it's going to work in the real world. So the Ekman transport is important, and the spiral and the surface flow are sensitive. This is what we said Nansen, this guy, was observing the ice flowing to about 20 degrees, icebergs flowing to about 20 degrees to the right of the wind. Ekman's simplified theory gives you, even though it's a complex theory, it still simplifies the fluid dynamics, gives you 45 degrees to the right of the wind. There's some discrepancy between these. We don't really care too much about the discrepancies. It's really if we just focus on the transport, we're going to be able to get some really robust answers that are going to be useful to think about how the ocean works on large scales. Okay, so the practical implications that we hinted at were along the equator, we expect upwelling because on the kind of northward side, we're going to get flow northward, Ekman transport northward. The southward side, we're going to get Ekman transport southward because that'll be to the left of the wind. And so this flow is diverging away from the equator. Cool. That's going to be an example of the kind of divergences we're going to be thinking about next. Similarly, if you go along a coastal region, you can get a divergence by pushing the Ekman transport offshore. And then the only thing that can really compensate for that is bringing up some deeper water up to replace it. And so you get an upwelling region along the coast if the winds along the coast are equatorward. That works in both hemispheres, and you'll get an upwelling region. And as we said, this equatorial upwelling region and the coastal upwelling regions are really important for productivity because this water that's being brought up is nutrient rich. So you bring up nutrient rich water into the light, and then there's a big bloom typically in this upwelling region all around the world on most of the west coasts of the continents. And then this is the one I want to focus on today, is really the consequences of what happens when the winds change direction from place to place. So if we have this pattern of winds on the left, where you have, say, a wind going this direction next to a wind going this direction, and you wrap your fingers around, use the right hand rule and start with one arrow and then wrap your fingers around to the other arrow to take the curl of that wind stress. Your thumb points down, and we showed last time that the curl of the wind stress, like this, or the wind stress really over the Coriolis parameter, but the wind stress, curl of the wind stress gives you the Ekman pumping velocity, the vertical velocity at the base of the Ekman layer. So in this configuration, you have a negative curl and a negative Ekman vertical velocity. In this configuration, you have a positive curl and an upward vertical velocity at the base of the Ekman layer. So pumping with a negative wind stress curl, suction up into the Ekman layer with a positive curl of the wind stress. The beautiful illustration that they have of this effect in the Collings book really focuses on the kind of curl character. Like imagine if you have really a cyclonic wind pattern, like maybe a hurricane. What happens? Well, that hurricane is going to drive outward Ekman transport all the way around. So this is cyclonic in the northern hemisphere. It's counterclockwise. And so you have Ekman transport to the right. So everywhere you're going to have transport out, you have a big divergence here in the middle, which means that you're going to get upwelling and surface flow out away from the center of that hurricane or big cyclone. If you have an anticyclonic wind, like a blocking pattern or something like that, then you have an anticyclonic pattern which pushes all the Ekman transport to converge into the middle here, which would cause a downwelling and a surface convergence. So the cool thing about these diagrams is not only that they make it really clear that this curl could be a circular thing and therefore trigger an Ekman velocity, but they also are drawing on both the sea surface and the picnic line. So when you have an upwelling pattern, you pull that deep water up, you make the picnic line approach the surface. And so you have anomalously cold, dense, salty water, typically closer to the surface than normal. And you have a sea surface height that is lower than normal. You have a sea surface depression. because you're pushing that surface water out and pulling up deep water to replace it. If you have a convergence and the convergence doesn't leak out the sides, you're going to tend to have a sea surface height anomaly where you have extra high sea surface and you're going to push down the picnic line away from the surface. So you have a kind of thick Ekman layer in this case. And you have a very thin Ekman layer in this case. The thin Ekman layer is going to bring the picnic line up to the surface and the sea surface height down, and the thick Ekman layer is going to do the opposite. So I hope that's clear. Let's see what that looks like when we think about the wind pattern of the real world. But first, are there any questions on this? Okay. So what do the winds look like over the whole of the Earth? So those of you who've done some atmospheric dynamics may have seen a picture like this. This is actually a really old-fashioned wind product that came out of, this is like from the 80s. So this is from before we had satellite winds from a scatterometer that we talked about. This is kind of almost the Ben Franklin or Matthew Fontaine Maury version of where the winds are in the world. This is like ship observations based winds. But why I like it is because there's lots of room between the wind vectors. So we're going to draw on top of this and try and highlight the general patterns. But you can see already that the general patterns is in the 40 degrees north. The winds are from west to east, that is westerly, and 40 degrees south, there are also westerlies. So these are sometimes called the roaring 40s because they have strong westerly winds in both hemispheres. Roaring 40s. The other big strong winds that we see are the trade winds, which are around the equator, a little bit north and south of the equator as well, that are easterlies. They're coming from the east to the west. So I'll take a quick aside. Oceanographers like to talk about where things go in currents. So we tend to talk about westward currents or eastward currents. Atmospheric scientists like to think about where the storm systems are coming from. So they talk about westerly winds that come from the west or easterly winds that come from the east, bring systems to you. So it's a little bit confusing because westward is minus westerly and eastward is minus easterly. And so frequently we have flipped conventions for like which is a positive and which is a negative. I try in this class to be consistent to use eastward as the positive direction and northward as the positive direction. So westerly winds are also positive and southerly winds are also positive. So, but you should be aware that there's a convention difference. So sometimes you may be reading an article and be like, wait, westerly? Is that right? Isn't that going westward? No, it's going eastward because there's a westerly is an eastward wind and an easterly is a westward wind. I think I just said the same way twice. But anyway, you get what I mean. Okay. So what if we just highlight in a big, strong arrow those westerlies and easterly patterns of the roaring 40s and the trades? So notice that we have that alternating wind pattern that we just talked about causing convergences or maybe divergences in the Ekman transport. So here are the kind of broad patterns of the winds. Here are the Ekman transports they would induce in the surface ocean. And so you can see that the Ekman transports would tend to be in the north-south direction, while even though the winds are in the east-west direction. That's exactly what we're saying, that the Ekman transport is perpendicular to the wind direction. Okay, so now look at those arrows, the purple arrows now, and notice that they're converging in some places here, and they're diverging in other places, like down here. So let's label those. Let's think about whether those are cyclonic and anticyclonic, convergences and divergences, and label them. So here is that kind of pattern. It's not shown here, but if we thought we were looking, say, westward in this figure, this would be sort of the pattern of the westerlies and trades in one of those northern subtropical regions. I should have said these regions are called the subtropics because of these patterns of winds. These regions are called the subpolar regions because of these patterns of winds. And then the equatorial region is kind of narrow in between the subtropics. So this is if this direction was looking westward, this would be kind of a subtropical pattern, and this might, if we're looking westward here, this might be kind of a subpolar pattern. What about in terms of cyclones and anticyclones? Let's go back. This pattern here in the subtropics is an anticyclonic pattern. Anticyclonic pattern in the southern hemisphere, also anticyclonic pattern. Anticyclonic pattern of winds, anticyclonic pattern of winds. So all of the subtropical regions share anticyclonic winds. What about up here? Well, up here we have cyclonic winds, cyclonic winds, cyclonic winds, cyclonic winds, cyclonic winds. All of the subpolar regions share cyclonic winds. And notice that I'm flipping the direction that I'm calling cyclonic between the hemispheres. Cyclones go whichever way they go in the hemisphere. They rotate like their pole rotates. But cyclones in the northern hemisphere are counterclockwise, and cyclones in the southern hemisphere are counterclockwise, just like the North Pole is rotating counterclockwise and the South Pole is rotating clockwise. Okay. So cyclonic winds tend to drive a divergence. So all of those subpolar cyclonic regions are going to be diverging. So we're expecting deep water, the picnic line, to come up towards the surface and low pressure in terms of the sea surface height, low sea surface heights in all the subpolar regions. By contrast, all the subtropical regions are converging. So we expect there to be a sea surface high, a high in the sea surface, and a depressed picnic line in all of the subtropical regions. So convergences, divergences, divergences. And now you can see that even though these are really different ocean basins, we're expecting them to converge and diverge kind of consistently among all of the different basins. Even the Indian Ocean has the small converging region here in the North Indian Ocean, even though there's not too much North Indian Ocean to have it in. The Indian Ocean is actually a really interesting one because this wind pattern changes a lot with the monsoon. And so it actually kind of flips directions as to whether it's converging or diverging depending on the season. So even though we're drawing these simplified winds up here on this end, on the North and Northern Indian Ocean, the winds are very variable with the seasons. So there's no point in putting a big arrow because it would have to change by season. The big arrows we put in the rest of the places are pretty consistent across the seasons. Okay, so let's watch some movies again. So here's our movie showing upwelling or showing chlorophyll on the left and sea surface temperature on the right. So what do you see about all of the subtropical regions? Play it again. Subtropical regions, are they high or low in chlorophyll? They're low. The equatorial regions are high in chlorophyll because of the equatorial upwelling, but the subtropical regions have these convergences in them. So the surface water is being pushed down and away, and it doesn't have a local source of nutrients to refresh it. So biologists call those oligotrophic regions, which basically means nutrient limited regions. And then, so the subtropics and the Mediterranean, you can also see here, and the Northern Indian Ocean, at least in some seasons, tends to have low productivity, low chlorophyll levels for that reason. What about the subpolar regions? High or low chlorophyll?
Hi.
There we go. High. High chlorophyll because there's divergence, surface divergences that are bringing that pycnocline up to the surface, maybe doing some mixing into it, bringing the nutrients up into the light, and you get blooms there. So not only is there upwelling driving coastal and equatorial upwelling that is important for productivity, but there is large scale divergence and convergence patterns that are driving productivity in the chlorophyll over entire ocean basins. The same is true, although it's not quite as obvious in surface temperatures. You can see that the temperatures are anomalously cold or anomalously warm, depending on whether you're bringing up or pushing down the surface layers, at least to as deviations from their kind of latitude average temperatures. Oops. So you might think, well, how can we observe those convergence and divergence patterns in some simple way to make ourselves confident that this whole sort of Ekman theory isn't being overrun by some other converging or diverging pattern? And you can, not in a nice way necessarily. We used to talk about the Sargasso Sea, which is sort of the convergence zone of the North Atlantic in the subtropics. And so that convergence zone brings sargassum, these big seaweed clumps together. But in the modern time, we talk about the garbage patches. So where does the plastic and marine debris accumulate in the world's oceans? So this video shows an ocean model which has all of the physics that we're talking about, and then they release buoyant drifters uniformly all over the world, and we're just watching to see where they collect. And you can see in those upwelling regions in the equator and along the coasts, those buoyant, plastic pollution, if you want, are driven out of the upwelling regions, the equator, along the coasts, and in the subpolar regions, and they're converging as the intensity is getting higher and higher into these garbage patch regions. Let's watch it again. They move and converge into the garbage patch regions, which are the subtropical convergences. So now see, we have the subtropical convergences are all highlighted. That's where the buoys are going first into all 5 of them. And then as the model runs farther into the future, so beyond year 10, it takes 10 years to pile them up into the convergences. And then as we run hundreds of years into the future, they slowly drain out of the weaker convergences and end up in the Pacific subtropical convergences, which is in fact where the strongest garbage patches are. So we already have the fluid dynamics and understanding of the garbage patches and where they're located and why. Well, the why is because humans have produced too much plastic that's buoyant, but the where is because of the wind patterns and the patterns of Ekman transport and where those tend to converge. Okay, so let's switch gears now a little bit to stop thinking about drifters and surfaces and start thinking about pressure. So we said that the sea surface height was going to be low in the divergence regions and high in the convergence regions, because if that water converges and doesn't drain away, it's going to pile up the surface where the Ekman transport is converging and deplete the surface height where the Ekman transport is diverging. That's true also along the upwelling zones. You would have a low pressure along the upwelling zones along the west coast of the continents, like the California current and the Peru current or the Humboldt current, those would also have low sea surface height for almost exactly the same reason. The sea surface height along the equator is harder to manage because there are things like El Nino that are coming along and making it wobble up and down with waves. But that's a story we'll come to later. But in these subtropical regions, you expect to have high sea surface heights, and subpolar regions, you expect to have low sea surface heights. So let's think not only about the pressure, but what happens to the picnic line. Um, this is a map from an ocean model of the mean hydrostatic pressure at 5 meters below the surface. We looked at this before, but let's look at it a little bit more closely. So 5 meters, it's not 5 meters below the surface, it's 5 meters below the average surface. So in pressure in decibars, 5 meters would be 5 decibars. So 5 on this means you have the pressure that you'd have minus all of these regional deviations. But this model's run with realistic winds, so there are regional deviations. So where in the world are the high pressure regions here?
In the ocean.
The high pressure ocean regions. So the sea surface height regions, so that the ocean near surface pressure is high because the sea surface height is high. So where in the ocean?
Um, well, I don't know how to point, but like in the middle of the Pacific, and then the north and then south. There are two different ones, and also
Exactly.
Atlantic.
The subtropical North Pacific, the subtropical South Pacific, those same regions where we have the anticyclonic wind patterns, which are causing Ekman transport convergence. Same is true in the Atlantic. We have a high in the North Atlantic and a high in the South Atlantic subtropical regions. So all of the highs here are in subtropical regions. There's a little bit of a low in the equatorial region, comparatively anyway, and there are big lows in the subpolar regions. And so these deviations in sea surface pressure and near surface pressure represent about 1 to 2 meters of vertical sea surface height anomalies. This is the time mean pressure field. So these sea surface and height anomalies are there permanently because the winds are just blowing and blowing and blowing and piling up the water into the subtropics and pulling it out of the subpolar regions. It's not centered the way that we kind of implied here, that it would be centered in the middle of each ocean basin. It's a little bit displaced to the west. So consistently in all of the basins, the either high anomaly or low anomaly is a little bit to the west. So this is going to be figuring out why that is going to be the topic of our third paper about westward intensification. But that's to come. Right now, you can just see that all the subtropical ocean basins are consistent and all the subpolar ocean basins are consistent in terms of their pressure. If we go deeper, this is now the same thing, the mean pressure at 1,517 meters, average depth in decibars. Most of those high and low anomalies have disappeared. You can see that there's a funny anomaly in the Mediterranean because we're below the sill depth of the Mediterranean. So that's a pressure that has to do with the density of the Mediterranean. And you can see that down here in the Southern Ocean, that low pressure is actually really persistent. The low pressure anomaly goes even to 1,500 meters and below. But everywhere else, we don't see at least as strong of a pressure gradient as we saw from location to location in the near surface. That makes sense to everybody? So it's kind of like a table, a flat table in terms of pressure with a drop off here to a lower pressure region around Antarctica.
I have a question.
Sure.
In the previous slide, this is measuring the depth at like 5 actual meters, or I'm a little confused about what is the relative depth.
Yes. So this is really 5 meters distance from the geoid or the sea level pressure level, like 5 meters difference from where the ocean surface would be if the ocean was not in motion and not experiencing forces. The
Okay.
ocean is in motion and is experiencing forces from these winds, and so it doesn't sit where it would sit. So if you turned off all the winds and let all the currents die down, this would go to 5 everywhere. But it's the winds that we're talking about, those convergences and divergences are making the pressure bigger because there's an extra pressure, there's extra water on top of you. The sea surface height has gone up in the convergence regions and gone down in the divergence regions. So you're not at 5 everywhere. You're sometimes up at 6, kind of here in the subtropical regions, and sometimes you're down at 4 in the subpolar regions. Does that make sense?
Yeah, thanks.
When we go deeper, you would think that you'd be at close to 15, 17. It's a little different because it's not exactly linear, but sort of 1533 would be the kind of average here. But you can see that it's close to 1532 kind of everywhere, except here it's a little bit lower, and here it's a little bit higher. And here it's a lot higher in the Mediterranean. Okay. So when we talked about hydrostatic pressure, the hydrostatic pressure is the weight of the air and water above you. So we're not worrying too much about the variations in the weight of the air above us because we're talking about multiple meters of sea level rise, which is big compared to the atmospheric high and low patterns in terms of the pressure that it represents. And so the pressures we're talking about is really the weight above you divided per unit area. So what we mean here is that if the height is elevated, it means we got more water on top of us. We got heavier stuff on top of us, and that's why the pressure is higher than 5, what you'd expect at 5 meters. And if the surface is depressed, then you have less weight on top of you. So your pressure is actually below what it would be, what you would expect to have at 5 meters. So excess weight above you, deficit of weight above you. And then here you have kind of the weight you'd expect to have above you. Here in the Mediterranean, you have less weight than you expect to have above you, which means that this water must be anomalously light. The same is true of the Arctic. So that's because of the properties of the water in that particular basin that's coming down. And in here, you have I said that backwards. Higher pressure than expected here. So these are anomalously heavy waters on top of you. And then here down in the Antarctic, you have exceptionally low pressures. So somehow there's less water weight on top of you. So it's helpful to go back to this little stack of bricks and stack of pillows that we thought about before in terms of measuring weight. And so this is an analogy for low density water. And then it also has the height of that low density water. So this stack of pillows is like you have a tall stack, so a sea surface height anomaly upward of light water. Whereas this little stack of bricks, it's shorter, so the sea surface height anomaly is low, but you actually gain pressure faster because the bricks are heavier, they're denser than the pillows. So if you had a tall stack of pillows, you might arrive at the same pressure at the bottom that you have as a short stack of bricks. So there's a compensating effect between the density and the sea surface height anomaly, or the depth over which you're going, that's kind of implied by this hydrostatic pressure relationship. Okay. So we not only have sea surface heights coming up and down, we saw that the pycnocline, so the density, which is often generated by a thermocline, is going up and down from place to place. Because as that Ekman converges, it's pushing the pycnocline up and down. And so there's a sort of secondary effect that we need to think about. The pycnocline could also be a halocline if you're in the Mediterranean or the Arctic or the Indian Ocean, some places that have a lot of strong hydrology forcing, but typically it's a thermocline. So sometimes I'll use thermocline and pycnocline interchangeably, but really we should be talking about the pycnocline when we're talking about the weight, because the pycnocline is the one that talks about where the density is. Okay, so here's our imagined subtropical gyre, a schematic. It's got a sea surface high because there is a anticyclonic wind, which is driving a converging Ekman transport pattern. And so we have an anomalous light water blob here near the surface. So we have a tall stack of pillows in the middle, and then we have a shorter stack of pillows on the side. And by tall and short, I mean the top of this stack of pillows is like the sea surface height, so it's up high. The top of these stacks of pillows is a little bit lower. So if I cut through the middle of these stacks of pillows, where is the pressure? The high pressure. Is it in the middle of the pillows or on the edges of the pillows where the high pressure is at kind of this average depth?
In the middle.
It's in the middle because this is higher up. So if you cut through, you got more pillows on top of you than you do here, right? You've only got this high of pillows, so there's only this much dense water on top of you here, and there's a lot more here. So that's exactly what I mean by this figure. 5 meters down, partway through the pillows, we see tall stacks of pillows here in the subtropics and low stacks of pillows around the edges, where we have the same pattern as this. Tall stacks of pillows here in the center of that subtropical pattern, low stacks of pillows on lower stacks of pillows at the top onto the sides. So the high pressures we were just talking about are because the sea surface height is higher above us or lower above us, like that. What about the pycnocline? So the pycnocline here is depressed downward, which is the same as that convergence effects. It's lifting the surface up and it's also pushing the pycnocline downward. So this middle stack of pillows actually goes deeper. The light water extends deeper than the light water on the sides of that convergence region. And when we get below the pycnocline, we start counting up dense water, bricks. So the pressure starts accumulating, even though the pressure right here is lower than the pressure here. As soon as we crossed into the pycnocline, the pressure starts accumulating, the weight starts accumulating faster than it is here because the bricks are denser than the pillows. So what do you think the pressure is like if I go below the pycnocline and cut across? At the near surface, it's high in the center, low on the edges. After I've let the bricks accumulate weight for a bit, what happens? The low pressure anomalies are being added pressure to faster than the high pressure anomaly was. So what do you think the pressure's like at the bottom?
Similar.
Pretty similar. And that's what we're seeing here. That high pressure anomaly next to the low pressures, once you go below the pycnocline down to 1,500 meters, the pycnocline anomaly is basically leveling out the pressure again. So the pressure below the pycnocline has very little horizontal gradient, and the pressure above the pycnocline has big horizontal pressure gradients that are centered on the convergence regions or lows that are centered on the divergence regions. That makes sense. So when we look at this pattern, we've got high pressure between the surface and the pycnocline, low pressure between the surface and the pycnocline in patterns that are representative of the overall planetary wind patterns. So the subtropics have high pressure between the surface and the picnic line. The subpolar regions have low pressure between the surface and the picnic line. And then when we go deeper, a lot of this pressure variation gets washed out by the cancellatory effects of the heaving of the picnic line by the same convergence and divergence patterns. Does that make sense to everybody? So in this story, then we've connected the winds to the Ekman transport, to the convergences and divergences, to the patterns of pressure in between the surface and the picnic line and below, with essentially these kind of simple diagnostics. So that was all I really wanted to talk about today, except we can go back through the review of balances again. Are there any questions on that? Okay, so let's go through our review of balances, but let's go through it with a little subtle change. Which of the balances involve the pressure? So Taylor-Proudman theorem involves these three terms. Is the pressure involved here?
It appears that it is.
It appears that it is.
There's a P in a gradient.
There's a P inside the gradient. It's a little complicated because I subtly split this one in half. So the normal gradient of P over rho, I pulled the rho inside and put it on this one, and then did the correction that I need to do. So I gain an extra term if I pull the rho inside, and this is the term that I gain. This one is going to be the one that has to do with the sea surface height variations or barotropic variations. This one is going to be the one that has to do with the baroclinic variations. That is the deviations of the picnic line depth. So the cool thing here is that the Taylor-Proudman only sees the sea surface height variations, but not those picnic line variations. And we're going to see what that implies next time when we start talking about geostrophy. These two terms behave really differently. One goes with the sea surface height and one goes with the interior density variations. And they're going to be the one, these two canceling out is what's going to work at depth, but near the surface, this one is going to be the dominant one. So Taylor-Proudman is going to be a big part of our story when we get into the next layer to talk about the pressures and what they imply. No pressure here in the inertial oscillations. So inertial oscillations are not going to have a lot to do with what the consequences of that pressure field are going to be. Similarly, the Ekman layer doesn't involve the pressure itself. It involves the Coriolis term and the viscosity. But as we saw, the movement of water induced by this can affect the pressure field. So even though the Ekman layer balance doesn't have pressures in it, it doesn't mean that the Ekman layer can't affect the pressures by causing convergences and divergences. The hydrostatic valence, of course, directly involves the pressure. It's the vertical pressure gradient, though, not the horizontal pressure gradient that's involved in the hydrostatic balance. So this is where all of our pillows and bricks are. They're just sitting here, balancing this term against this term. So pillows and bricks versus bricks comes in the row, and the accumulation of pressure with depth is how tall those stacks are. It's the gradient here being turned into a vertical derivative and then being integrated over. So this is where the whole pillows and bricks games is it's in the hydrostatic pressure balance. All right, that's it for today. So let me quit out of sharing. And if anybody has any other questions or anything else, I can take a few minutes to talk about that. I'm going to upload the video shortly. This version of the is probably a lot better than the one from 6 years ago that I posted as the pre-recorded video. So I'll replace that one with this one shortly if people want to go back and watch it. I'm going to stop the recording now.